Okay, so it's a pleasure to start today's seminar, 1st May. So it's a holiday for most of us, but here we are here working again. So we will have Elias Cueto from Spain and Shingi Ruan from Miami. So please, Ana, present Elias Cueto.
Okay, thank you very much, Lucero. Thank you very much, Professor Elias Cueto, for accepting the talk. So, Elias Cueto is a full professor of engineering at the University of Zaragoza in Spain. Actually, he is a chair on the National Strategy Project in Artificial Intelligence and Sustainability. His research interests include the development of numerical method for computational mechanics in its broadest sense. He has worked on finite element and meshless method or model order reduction techniques with application on forming process simulation, real-time simulation, computational surgery, and more recently on data-intensive computational mechanics, thermodynamics-informed neural network, and augmented mixed reality. He has several awards and honors. He is a member of editorial boards of many international prestigious journals, and he is a widely cited author. So thank you very much, Professor. And today he will present a talk entitled Recent Advance in Thermodynamic-Informed Neural Networks. So thank you very much, and you can start.
Thank you so much, Anna, for your kind introduction. Thank you for your invitation. It's a pleasure to be here today in this seminario. And well, as you mentioned before, my idea is to to present some recent results about thermodynamics-informed neural networks. First of all, please let me introduce my collaborators, the members of my groups, the people who really did the tough work that gave rise to the results I'm going to show today. Well, in general, it is well known that learning physics from data is a very challenging task that involves many difficulties, but it is very interesting from multiple point of view. For instance, starting from scientific machine learning, in order to unveil scientific laws, for instance, in order to develop cognitive digital twins, something that I will introduce in a moment, in the field of robotics, and many others. Our interest in this case is motivated by the development of digital twins. I'm sure that everybody in the audience knows what a digital twin is. It is defined in Wikipedia as a virtual representation of an object or a process that can serve to represent the evolution in time in a continuous way as a real-time digital counterpart of a physical of this physical object. In the screen, you are seeing a particular prototype of such a digital twin. In this case, of a beam made of foam. In this case, we are particularly interested in what we call the cognitive digital twins. Cognitive digital twins are digital twins able to see through computer vision, of course, able to understand what they see. This is called perception in the field of robotics. But more interestingly, they are able to make prognosis. Again, in the field of robotics, this is called reasoning, and this is done by real-time simulation. Finally, they are able to inform the human in the loop for decision making. And in our case, as you can notice in the video, we do this by augmented reality, by employing augmented reality. So the difficulties we face in this search is that in general, working with data mainly is usually done by black box methods. In particular, neural networks are the prototypical example. But humanity has been doing science since many centuries ago, so we already know a lot of physics. We believe that it is simply nonsense to discard of all of this scientific knowledge, and our research in the last years has been involved in how to introduce this scientific knowledge into this data-driven learning process. In particular, what if we know that conservation laws apply to some physical phenomena, if it is the case, strictly related to symmetries in the problem by means of the Noether theorem, or in general any other principle. Another difficulties we face in this problem is, for instance, at which scale should we describe a particular phenomenon? At which scale should we sample the data? A very frequent problem. Do we really have big data in engineering applications? This is very rarely the case. In social science, it's more often the case, but not in engineering. Data are expensive, difficult to obtain, to maintain, to store. So in general, we work in the scarce data regime. So how does all these affect the learning process? We are going to see it during this presentation. So let me begin very briefly by talking a little bit about the statistical mechanics of machine learning. This is how we set the problem. We see learning a physical phenomenon as finding the evolution in time of the state variables of the system. We group these state variables in this vector Z, and the objective is to find out the temporal evolution of this vector, which in general will be a nonlinear function f that will depend on time and on the state of the system itself, given some initial conditions. So we state the problem in the form of supervised learning. The objective will be to find the flow map that takes the initial state of the system, set 0, and maps it to set at some time horizon capital T. So what we do actually is to tune f by regression so as to find this flow map. This is the idea. This is the objective of this problem. Well, given this general framework, we can think of introducing physics in F. What if we know something about the physics taking place? For instance, imagine for a moment that we are able to go down to the molecular dynamics scale at which Newton laws apply. Newton laws are perfectly reversible. So we can think of assuming that F has a Hamiltonian structure at this scale. So in this case, the vector Z will be composed by the set of position and momenta of every particle in the system. If this is true, the evolution of a Hamiltonian system is well known, will be given by the product of the symplectic matrix capital L times the gradient of energy. The of course, big difficulty of this approach is that in order to obtain meaningful results, we need to consider the analysis of a big number of particles in the order of the Avogadro number, 10 to the 23. This is absolutely not possible with current computers. So in one way or another, we must think of coarse graining the problem to go to describe the physics at a more general, more coarse scale. Nevertheless, the interest in imposing conservation or reversibility in the predictions, well, has attracted a lot of researchers in the last year. This is a brief list, completely out of date, of papers trying to impose conservation in the description of a physical system learned by data. However, it is well known that if we coarse grain the system, if we move from a very high dimensional system like the one before, the molecular dynamics scale, defined in R to the capital D dimensions, and project it to a coarser space in small d dimensions, this has some important implications. First of all, ignored details influence observed variables, and this is well known since the times of Gibbs and James. And since several states at the micro scale give rise to the same state at the macro scale, projections into the future will introduce fluctuation in the predictions. And fluctuation is equivalent to dissipation by the fluctuation-dissipation theorem. So in other words, by coarse graining the description of our physical system, we are introducing dissipation in the system. Introducing conservation is very interesting, but in practice, almost everything in physics is dissipative. So is there any way to describe a system from data and enforce the right degree of dissipation in this description? This is the objective of our work today. Again, many authors have tried to do this. For instance, symplectic ODE nets. Several authors have tried to deconstruct inductive biases through Port-Hamiltonian neural networks. I will get back to Port-Hamiltonian approaches in a moment, but in relaxing equivariance, for instance. But in general, none of these works are able to satisfy thermodynamics by construction. So this is our objective. To introduce dissipation into this formulation and to do it properly, we need to introduce a new potential, entropy. Okay, so this gives rise to a so-called metriplectic, because it's at the same time metric and symplectic formulation that assumes that the evolution in time of our variables will be composed by two terms, one reversible and one irreversible. The reversible one has a Hamiltonian form, the symplectic matrix capital L times the gradient of energy, and the irreversible term has a similar structure with a friction matrix capital M times the gradient of entropy. This induces a bracketed structure in the problem. Okay, with the classical, the braces represent the Poisson bracket, and the brackets represent the dissipation bracket. The so-called generic formulation, generic stands for general equation from non-equilibrium irreversible coupling, introduces two additional conditions, the so-called degeneracy conditions, that in brief state that entropy has nothing to do with conservation, so L times gradient of entropy vanishes, and in turn energy has nothing to do with dissipation, so M times gradient of energy also vanishes. In order to enforce these conditions, it is enough to choose capital L to be skew-symmetric. This is classical since it is a symplectic matrix, and M should be symmetric and positive semi-definite. If this is true, we can demonstrate very fast that the evolution in time of the energy vanishes, which is the conservation of energy in closed systems, and equivalently, the evolution in time of entropy should be positive, which is the second, or non-negative at least, the second principle of thermodynamics. So by assuming that the evolution in time of the system takes this generic form, we are in the position of ensuring the compliance with the first and second principles of thermodynamics. Well, how do we accomplish that? By parameterizing L to be skew-symmetric and M to be symmetric and positive semi-definite. Since we employ neural networks to learn the particular form of Lm, the energy and the entropy, we establish a loss function related to the fulfillment of the experimental data. Another term, another loss, which is related to the fulfillment of the degeneracy conditions. And finally, the global loss will be composed by a combination of both through a Lagrange multiplier lambda that takes into account the relative importance of both terms in the loss. This can be imposed in this way in the field of neural networks. This is known as a soft imposition of the thermodynamic structure of the problem. It is possible to impose it in a hard way. After our work in 2021, several authors including George Karnadakis and co-workers, for instance, have developed equivalent formulation by imposing it in hard way. In hard way means by including these conditions in the architecture of the neural networks. So in order to show you how this works, let us consider an example. This is a tire that is rolling on the road and faces a step on the road. Okay, the tire is made of a hyperelastic rubber and internal pressure. And well, we have in this case synthetic data coming from finite element simulations. So since it is a very complex, very detailed finite element model, what we do first is to unveil the true dimensionality of the problem. So to do this, we employ a particular neural network architecture, which is known as autoencoders. An autoencoder is a neural network that learns the identity matrix, but passing through a bottleneck that should have the length, the dimension of the true latent dimensionality of data. In our case, we employ L1 norm autoencoder so as to enforce the obtention of the actual dimensionality of the problem. And once we have unveiled this true dimensionality of the problem, we split the network and construct in the middle the time integrator, the type of neural networks that I have just introduced, the neural network based in the generic structure that will integrate our latent variables in time. Okay. So to show you how this works, you have on the left the ground truth, the finite element simulation. On the right, you have the classical model order reduction to this problem made by proper orthogonal decomposition. You see that since the problem is nonlinear, classical linear model order reduction techniques fail to reduce the problem. You see some weird effects in the reconstruction of the problem, but how our neural networks reconstruct the problem very accurately. If we take a look to the errors made in this reconstruction, there are some important messages to highlight today. For instance, if we compare a black box neural network, the accuracy, which is not that bad, the mean squared error of a black box neural network is below 10 to the minus 3. That's not bad. But if we introduce the right thermodynamic structure of the problem, we see that the mean error is below 10 to the minus 5, 2 order of magnitudes beta. Even if we introduce some noise in the data, the predictions of our neural networks are still very, very accurate. And even if we don't constrain these networks with the fulfillment of the degeneracy conditions, we assume the metriplectic structure of the evolution in time, but don't enforce the degeneracy conditions, the networks are very robust. Okay, so what we see actually in this graph is that the more physics you introduce in your problem, in your learning problem, the more accurate your results will be. And in general, the less data you will need, which is, if we think of sustainability, is of course very, very important. Well, recently we have checked different architectures, and in particular we find that graph neural networks are an appealing choice in this task of learning physics from data. Graph neural networks are very interesting. In general, they assume that the system under study has a graph structure, and since in general we employ synthetic data coming from finite element simulation, it is straightforward to identify a finite element mesh with a graph. Okay, so in a finite element mesh, the nodes carry the essential variables of the problem. That could be position, velocities, stresses, pressure, temperature, whatever, depending on the particular physics. So the graph will be composed by three sets: the set of vertex, the finite element nodes, the edges connecting this vertex, and a global feature set of the problem. In general, we employ the edges to encode the relative distance between the nodes in order, not the position, but the relative distance, in order to make it translation invariant, in order to enforce Galilean invariance in the predictions of our networks. The vertex of the graph will carry, as is the case in the finite element models, so to speak, the essential variables of the problem, stresses, displacement, whatever. And finally, the global vector U includes parameters of the problems: gravity, Poisson ratio, Reynolds number, etc. Well, what is interesting is that in a graph neural network, we consider two networks actually. Every node shares the same neural network on one side, and every edge shares a second neural network. Okay, so the learning process has an encoder processor decoder scheme in order to finally obtain the form of the matrices small l and m that give rise to capital L and M, the matrices of the metriplectic formulation of the problem. And on the other side, they are able to learn the energy and entropy potentials of the problem, that by computing the gradients will allow us to obtain the next time updated form of the vector of state variables. So in order to check how all this works, we compare for two different problems the flow of an Allroyd B fluid and beam bending problem. We compare our original thermodynamics informed neural networks, which we call a structure preserving neural network originally, which include a metriplectic bias, but not a geometric one. We don't assume any graph structure. We compare them with the original work on graph neural network, but that don't consider the metriplectic bias, but includes the geometric one, the graph structure. And finally, we combine both, okay? Well, for the Cueto flow of the Allroyd B viscoelastic fluid, in this case, our set of variables includes the position of the nodes, the velocity, horizontal only because it's a shear flow, the energy, and the extra stress tensor in the fluid. We cover a range of Reynolds number between 0.1 and 1, and a range of Weissenberg number between 1 and 2. Weissenberg number takes into account the degree of elasticity of the fluid. The conclusion is very similar as in the entire problem. For the position, velocity, energy, and conformation tensor variables, we see that in general, the more information you add to this learning process, the better the results you obtain. Always our approach improves the result of existing networks, and for every magnitude the accuracy is remarkable, particularly in the prediction of the position. We are in between 10 to the minus 2 and 10 to the minus 3 in relative error. For instance, the flow past a cylinder problem, a classical problem in fluid mechanics. In this case, since it is a Newtonian fluid, no need to consider the extra stress tensor as a state variable. The velocity and pressure is enough to describe the problem. And again, you see that our approach that includes the thermodynamics biases and the graph structure of the problem improves by far the results of existing neural networks. But what is interesting in this case is that by identifying a finite element mesh with a graph, and by using this kind of graph neural networks, we can modify the mesh in a finite element model. For instance, change the position of the obstacle in the flow, and in some sense, this type of graph neural networks are able to learn the physics. Even for a position of the obstacle not seen before, not included in the data, the accuracy of the prediction is remarkable. You see in the bottom figure the ground truth, the finite element, finite volume in this case, I think, result, and how for this particular position of the obstacle, never seen before by our networks, they are able to provide very accurate results in really fast time. So let me continue with the so-called port metriplectic neural networks. So far, we have imposed energy conservation in our system because it's a closed system, and the right amount of dissipation. But what happens is the system is an open one. Okay, this is very interesting for complex systems. For systems of systems made of pieces that in general obey different physical laws for multi-physical systems, multi-scale systems. So what happens if we have one of such systems of systems? In this case, well, we are interested in learning the physical evolution of each subsystem separately. But in this case, since all of them communicate and transfer energy and entropy between them, they are actually open systems. So in open systems, the Poisson bracket and the dissipative bracket will have a bulk term and a boundary term. They communicate, they transfer energy and entropy through the boundary. So the evolution of the open system will be composed by the combination of the bulk and boundary terms. Okay. For each of the systems, of the subsystems, their evolution is actually the bulk evolution will be the total evolution minus the boundary contribution from nearby systems. Well, this generalizes the port Hamiltonian. This is a mistake here, not port multiplectic. This is a port multiplectic approach, generalizes the port Hamiltonian formalisms and guarantees the right thermodynamic structure even for open systems. Okay, you see here a classical problem. It's a double thermoelastic pendulum. It's a double pendulum in which the springs dissipate energy, dissipate heat by means of the Joule effect. Okay. In this case, our set of state variables is composed by the position and momenta of both masses and entropy of each one, of course. Well, this is a toy problem in which we have considered the possibility of solving two 5 degrees of freedom models instead of one single problem with 10 degrees of freedom. In general, considering this approach gives exactly the same amount of accuracy as the closed system approach, and gives rise to the possibility of learning the system by pieces. Okay. Consider, for instance, a system made of two cantilever beams, and in which we learn the behavior of one single beam and combine both. Again, you see that the accuracy of our approach is remarkable, and this kind of networks solves the problem so fast that we can consider the possibility of employing this type of approach for augmented reality or mixed reality applications. Okay, you see here two virtual beams that don't exist, but nevertheless interact with, in this case, the hand of Kelkus Hernandez, my former PhD student. Okay, we have learned from data one of these beams, but the system is actually made of two of them, and you see here how both interact and exchange energy and entropy. These are viscous hyperelastic beams, so they dissipate energy. Examples. Well, for instance, a problem with interest in aeronautics, the sloshing of fuel in the deposit of airplanes. Okay, this is an experimental setup in which you see a deposit not fully, not completely full of liquid that is subject to some oscillation as if it were in the wings of a plane. Okay, so here we consider two different physics. On one hand, the oscillation of the wings, that in general will have some degree of dissipation, and on the other, the sloshing of the fuel in the tank. In this case, we didn't employ a neural network. We prefer to test if it was possible to learn this type of systems from data, but by employing classical linear regression, piecewise linear regression, we employed MATLAB by using the classical f-min-con function of MATLAB, and locally linear embedding interpolation and a nonlinear interpolation scheme on the manifold of results. We first characterized the structural response of the tank. As I said before, the wings of the airplanes have some degree of dissipation, very low, but they are not perfectly elastic. And then we tested some degrees of filling in the tank. Okay. The idea is, of course, to be able to predict the behavior of the tank for any degree of filling. So we first characterized the tank as a without any fuel, a dry tank as a closed system. Okay, you see that the vibration in the wing, of course, will disappear if we wait time enough. And then we tested 10, 20 until 90% of filling of the tank. The objective is to make accurate predictions for any other filling level in the tank. Here we perform interpolation in the manifold of dissipation matrices. Okay, the Poisson matrix is assumed to be constant, so the influence of the different degrees of filling of the tank will be assumed to influence the value of the dissipation matrix. Interpolating these M matrices by taking into account the degree of filling as the main variable does not work. This is a very nonlinear problem. So the idea is to employ this kind of locally linear embedding approach so as to interpolate in the manifold of the result, not in the Euclidean space. Another example of fluid structure interaction. This is an experiment in which a cantilever beam is handling a deposit in which some water is oscillating. The beam, of course, is subject to bending and also to torsion, which induces the oscillation, the sloshing of the water in the deposit. The tank is assumed to be rigid. For this case, it is enough. And you see here the reference result on the left and our learned results on the right for some degree of filling of the deposit not seen in the experimental data. Okay. Again, the results you see here on average are around 3 times 10 to the minus 3 for the L2 norm relative error. Very accurate results in the prediction of the results. So, in conclusion, what we think is interesting of this approach is the possibility of learning the physics of some system or process and still be able to guarantee the fulfillment of the laws of thermodynamics, conservation of energy, and the right degree of dissipation of entropy. This approach has been demonstrated that generalizes very well to unseen situations, and particularly the graph neural network approach is very interesting when working with data coming from finite element simulation, synthetic data. And as I said before, the take-home message of this work is that in general, the more physics you add to the learning procedure, the less data you need, the more accurate your predictions will be. Finally, we have developed a generalization of port Hamiltonian systems, giving rise to what we call the port metriplectic approach, that still has the right thermodynamic structure for open systems. So finally, some acknowledgements to our funding institutions, in particular the government of Spain, the French company ESI, and in this case also the US Army. And well, I'm open for any questions. Again, thank you so much for your kind invitation. And if you have any question or doubt, of course, in our web page, you will find a lot of documentation about these results and other, including preprints, so on. If you are interested, of course, feel free to drop me an email, and I will be glad to send you any reference data code if you know it. So thank you.
Okay, thank you very much, Elias, for this wonderful talk. So let's ask to the audience if they have some questions to you. So please. Yes, you can use your microphone or chat.
Good afternoon. I would like to make some question for the team.
Okay.
Of course.
For capture the date, the real date. En otras palabras, me gustaría saber para captar los movimientos reales qué máquina está usando, ¿no? Porque supongo que esos datos le va a servir para introducir y obtener una simulación real, ¿no? O estoy equivocado.
Bueno, contesto en español en este caso. No estoy seguro de haber entendido la pregunta. No sé si se refiere usted a alguno de los ejemplos en particular.
Por ejemplo, el problema del péndulo. Si
Sí.
yo capto los movimientos, lo puedo hacer con un aparato, por decir, y después reproducirlo, porque como es la data real que yo tengo, que después lo voy a simular. Como usted hizo el
Claro.
movimiento, claro.
Sí,
¿Cómo
sí, ya entiendo. A ver, aquí hay un problema sobre el que no he mostrado resultados, y es que en general este tipo de formulación metripléctica necesita datos tanto de desplazamientos, velocidades, etcétera, como de tensiones, fuerzas, es decir, necesita variables tanto en el fibrado tangente del problema como en el cotangente. En general, obtener datos sobre tensiones, etcétera, es muy complicado, cuando no directamente imposible. Y es por eso por lo que muchas veces nosotros trabajamos con resultados, con datos sintéticos que vienen de simulaciones hechas con elementos finitos, con volúmenes finitos. Una vez entrenado el sistema, sí que es verdad que nosotros podemos corregir las predicciones una vez que tenemos observaciones sobre el sistema. Pero primero hay que hacer un entrenamiento teniendo en cuenta todas estas variables. Y a veces no es fácil obtener todos estos datos y no queda más remedio que hacerlo mediante simulación.
Ok, disculpe, una cosa final. Ahí veo que usted también ha hecho una regresión. Significa que ahí sí tiene que hacerlo con lenguaje R o MATLAB
En
o
este
no sé
caso
qué,
MATLAB, sí.
para justamente ver si la regresión lineal, ¿no? Si los
Sí.
errores residuales son menores, todo ese análisis, ¿no? De ajuste de modelo, mejor dicho, ¿no? ¿Eso
Sí,
sí?
sí. Completamente. Es regresión lineal a trozos. No es una regresión lineal clásica, sino que es una regresión lineal a trozos, donde la evolución en el tiempo del sistema se discretiza en incrementos de tiempo relativamente pequeños, y por eso somos capaces de predecir la respuesta no lineal del sistema. No es puramente una regresión lineal, sino una regresión lineal a trozos.
Claro, entonces Bueno, en todo caso, esa base de datos no es muy entesa, o es dato por decir. ¿Se puede decir qué tamaño de datos es? ¿1000, 2000? ¿Tiene un
Bueno,
tamaño?
depende del problema. Por ejemplo, recuerdo perfectamente el problema del neumático viene de un modelo de elementos finitos con aproximadamente unos 3500 nodos, a 3 grados de libertad por nodo, y está resuelto, no recuerdo exactamente en cuántos incrementos de tiempo, pero probablemente en unos 800 o una cosa así. Entonces,
Ok,
bueno,
muy agradecido.
estamos
Entendible.
trabajando, es algo que no he enseñado hoy porque, bueno, no quería excederme del tiempo asignado, pero estamos trabajando en el desarrollo de técnicas para trabajar en el régimen de pocos datos, es decir, no en el famoso Big Data, sino cuando tenemos muy pocos datos. ¿Qué pasa cuando tenemos muy pocos datos? Pues que, bueno, si conocemos parte de la física que rige el problema, podemos suplir esa carencia de datos con nuestro conocimiento previo, claro.
Pero una cosa final, de todas maneras ustedes ajustan, creo, ecuaciones estocásticas, también ahí veo, parece, ¿no?
En
La
general, no.
fluctuación.
El modelo generic admite una extensión estocástica. No hay ningún problema en generalizarlo a un marco estocástico, pero en general nosotros consideramos resultados que vienen de simulación y que son perfectamente deterministas. Pero no existe ni la más mínima limitación para considerarlos estocásticos.
Ok, muy agradecido, profesor Cueto, muy agradecido por la información.
Bien.
Muchas gracias.
Bueno, tenemos otra pregunta. We have another question from Professor Mejazais, please.
Merci, Anna. Thank you, Elias, for this impressive results. And okay, I'm going to ask a couple of questions, and my question will prove that the reality. I don't have any experience with neural network, and okay, I go. First question: one of the novelties comes from the fact that you are now using graph neural network. And I mean, when we decide about the graph, it has its own complexity, its size, okay? And I mean, when you start your computation using GNN, is it easy to compute? I mean, do you need, I mean, for example, when I try to make simulation using finite element, I know I have to try with to respect some parameters like size of number of finite element. I can run 3-4 times before finding the right condition and to run. And once I found this, I can run several times. I mean, when you go with this technique, I mean, is it easy to learn how to use it, or is it immediate, or we have to learn the sense of
Yeah, there are a lot of things to comment about this question. It's a very, very interesting question. In general, the answer is manifold. Okay.
Okay.
First of all, we assume a direct identification between the finite element mesh and the graph of the network. Okay. The question is that in general, this kind of graph neural network do not scale well. Okay, if you consider, for instance, a state-of-the-art finite element model composed by millions of degrees of freedom, which is nothing spectacular, is the standard in today's industry, you won't be able to solve with a graph neural network including millions of degrees of freedom. They scale hardly to such big problems. We are working on it precisely by employing a port metaplectic approach to the problem, but in general it is an open question, and a lot of groups worldwide are working in scaling graph neural network to bigger problems. Okay.
Okay.
So first of all, if you have a very big finite element method, you will need to reduce it in some sense in order to be able to feed a graph neural network with this structure. It's not evident how to do this, and it's nowadays the most important limitation of graph neural networks. Okay. But as I said before, a lot of groups are working on this, and there is a result from DeepMind for weather report applications in which they develop very detailed models of the Earth for weather prediction that are not exactly multi-scale, but I would say hierarchical. Okay, they begin with a very coarse description of the Earth and refine up to 8 times in order to obtain a very fine description of the Earth with very detailed description of the weather. This could be an interesting approach to develop hierarchical approaches. Start the simulation with a very coarse graph and refine the graph maybe with some adaptivity criterion in order to obtain the degree of accuracy you need. But at this moment, this is still an open question worldwide. Nobody has the definitive answer to this problem. So there is room for research. This is good news.
Okay, maybe just the last question, but it is more close to broma, or the joke than a real question. So you are informing neural network with the thermodynamics information. And I'm wondering, why is it possible to inform the classic basis like POD and PGD modes and to give this kind of information to the classic basis, or?
Absolutely.
Okay, so it's, I was not sure it can be done. Okay.
We began this approach by working with reduced order models.
Okay.
This was the origin of our research.
Okay, and you succeed.
We've been doing research in reduced order models for the last 15 years or so, and this is the origin precisely of this research line. So absolutely.
And you succeed to preserve structure?
Yes, absolutely.
Excellent.
Absolutely.
Okay, thank you.
So,
Merci.
well, there is one main difficulty. You cannot impose the metriplectic structure and then reduce the problem.
Yeah.
This will destroy the structure of the problem. But instead, first reduce the problem and then impose the structure. Okay, this is the only trick of the approach.
Okay, thanks, Elias. Thank you.
You're welcome.
Okay, thank you very much, Elias. I think we are out of time for other questions. I'm very interested on your work, especially on fluid-solid interaction. Probably I will write you email and we can interchange.
Please.
So thank you very much for being with us. And
it's been a pleasure. Thank you.
Okay, thank you very much.
Thank you.